Hi, in this video, we want to look at the introduction to mapping and function. During the course of the video, we'll be looking at the meaning of mapping, we'll be looking at the terms associated with mapping, we'll be looking at the types of mapping that we have. Out of these types of mapping, we'll be looking at the ones that can be classified as functions. And then we'll look at the meaning of function, how to write function, that is function notation, and how to substitute values inside of these functions. Then in subsequent videos, looking at the types of functions that we have, where we talk about the composite function and the inverse of a function. Then lastly, we'll look at the largest possible domain of a function, that is the largest value a function can attain. All right, so let's move on to what we have for this video. Now, what is mapping, or how can we describe mapping? In order to describe mapping, three things needs to be satisfied. First one, we must have two distinguished sets or two sets. Two sets. The second one, we must have a rule connecting the two sets together. And then the third one, the direction in which the sets are traveling. I repeat myself. Before we can describe mapping, before we can ascertain that, oh, this is a mapping, then three things that must be checked must be that, okay, do we have two sets? Is there a rule connecting the sets together? And then is there a direction between these two sets? Another word for mapping is relation. So instead of saying mapping a lot during the course of this video, I might be referring to mapping as relation. Think about it like relationship. Remember, before you can have relationship, you must have two people. Then there must be a clear defined goal, and then the, of course, power surge must be clearly visible. So think about that as mapping. So two sets, a common role, and then the direction in which they are going. So let's try and picture this. So let's say we have 1, 2, 3 inside of this circle, and then I have something else, 4, 5, and 6. So we're saying that we must have two sets, which is the circles I've drawn, the two circles I've drawn. Then we must have a common rule. That is, what am I doing to one of these sets to get the order and then the direction of the what's it called, of the path that this is going through. Okay, so now I can call this set X and I can call this set Y. So if I don't want to call this first one set X, I can otherwise call it my input. So why am I calling it my input? Because this is what I'm doing something to. You can see the direction, or the arrow direction. So I'm doing something to 1 to get me 4. I'm doing something to 2 to get me 5. I'm doing something to 3 to get me 6. So wherever the set you're doing something to, we can refer to it as the input or the domain. Input or domain, while the result or the output that we're getting from doing something to our X, we can call it the output or the codomain or the image, or sometimes we can call it the range. Sometimes we call it the range. All right, so two sets X and Y, or input and output, or domain and codomain, or image or range. Now, how about the rule? It must mean that I'm doing something to everything inside of X to give me everything outside of Y. So how do we get this rule, or how do we find this rule out? So what am I doing to 1 to get me 4, or what can I do to 1 to get 4? There are different ranges of things I can do to 1 to get 4. But what we are most concerned about is everything we're doing to 1, we must do to 2, we must do to 3 to get the same thing. It must be a common or uniform rule. So you can say to 1, I can say, okay, what exactly am I doing to 1? Maybe I'm adding 3 to 1. If I were to add 3 to 1, it gets me 4. That is 1 plus 3 will get us 4. If I add 3 to 2, I'll be getting 5. If I add 3 to 3, then I'll be getting what? 6. So it must mean I'm adding 3 to all my input values here. So if I add 3 to X, so I can simply say X plus 3 must be my rule. So Definitely, if we were to have 4, then the output here will simply be 7. If we were to have 5, the output would be 8. So I keep on adding 3 to whichever my input is. So you might just think about it like a machine that you are feeding in a particular number, and then that machine is perhaps adding 3 to the number, to the input you are bringing in, and then it's giving an output. So I can put in 1 here. 1 plus 3 gives me 4. So if I were to put in 2, 2 plus 3 gives me 5. If I were to put in 3, 3 plus 3 gives me 6. So that's what mapping is trying to tell us about. All right. Now, another term we need to know, or another term, since here we are using codomain image range output, why is range being asterisk? Now, let's say we have okay, but before we talk about that, people should take more examples on how to find the rule attached to mapping. So let's try and clear this so we can take other things. So let's say we have another set of mapping. Okay. All right. So this time around, so let's say we have 1, 2, 3. Then here we have 4. Here I have a dash. Okay. Then I'm saying, okay, 1 is mapping out to 4, 2 is mapping out to dash, 3 is mapping out to 12. Okay. Then we have a arrow diagram. Okay. Now, if we are to find this missing value, what can we say, or how can we find it? Again, we have to find the rule. Once we know the rule, then we can know what will be present inside of this place. So what am I doing to 1 to get 4? And what am I doing to 3 to get 12? If I were to say I'm multiplying 1 by 4, okay? So let's say 1 multiplied by 4, I'm having 4. 3 multiplied by 4, I'm having 12. So it must mean that this number in the middle here must simply be 8, because if I multiply everything here inside of this input by 4, then definitely I'll be getting what I'm having at this output. So if I were to write what 1 is mapping out to, inside or grouping them together, then I'll be grouping them in something called an ordered pair. Ordered pair. That is, I can say 1 is mapping out to 4. Okay, I can also say 2 will map out to 8. And lastly, 3 mapping out to 12. Okay, so far, the rows we've been using, we've been adding or we've been multiplying. But this is not how all the rows will be. Sometimes the rows might be a bit complex. So how do we now find complex rows? What are the things that you want to watch out for? Okay, so let's look at this other one. So let's look at another example. So let's say how to describe or how to find out complex rows as far as mapping is concerned. Okay, so let's say we're given so this one are given a particular value. So let's say we have 2, 4, and 6, and then it is mapping out to, let's do that properly. Let's say it's mapping out to 5, 11, and 17. So let's see, what am I doing to 2 to get me 5? And it must be the same thing I'll do to 4, that will get me 11. Must be the same thing I'll do to 6, that will get me 17. Okay, so what you want to watch out for is, okay, look at this. This is 2, 4, 6. The difference between them is 2. Okay, now 11 and 5, the difference between 11 and 5, 11 subtracted by 5 is simply 6. 17 from 11 is simply 6 also. So I'm having 6, 6 as the difference. So what must I be doing to, what's it called, to 2 to get me 5? Let's try and multiply 2 by 6. If I were to say 2 multiply by 6, I'll be having 12. Subtract 2 from it. Just multiply, subtracted by 2, I'll be having 10. So definitely this can be my rule. Why not divide this 6 into 2 equal parts? So divide 6 into 2 equal parts, we have 3. Now again, multiply 2 by 3, I have 6. Now the difference between 2 and 4 is 2. So divide that also by 2. Remember, we divided by 3. the difference here, and then this difference here we want to divide by 2 also. I'm going to come again. We divided the difference between 11 and 5, and 17 and 11 we divided by 2 to get 3. And the difference between 4 and 2, we are dividing it also, and we got 2. So dividing it by 2, we are getting what? 1. So let's try and multiply this 2 by 3. 2 times 3 gives us 6. And then subtract 1 from it, I'm having 5. Let's check here whether it works. 4 times 3, we're having 12. 12 subtracted by 1, we're having 11. 6 multiplied by 3, I'm having 18. 18 subtracted by 1, we have 17. Definitely, it must mean that what I'm doing to my input here, my input value, I'm simply multiplying by 3. So I can say 3x, and then I'm subtracting 1 from it. So if I have 3x minus 1, and then let's say, for instance, I have a value of 8 here, I can easily know my answer. So I'll simply multiply by 3 and then subtract 1 from it, and this will be 23. And if I also have, let's say, 9, then multiply by 3 also and subtract 1, I'll have 26 here. Oh, sorry, 20, that 26 here. Okay, so that's what we are having at this junction. I hope this makes sense. I hope this makes perfect sense. All right, so that's how we can determine rules for what's it called, for mapping. Now, you have to be watchful again. Sometimes the rows might be squares, square roots, cube roots, fourth roots, fifth roots. But note that the rule rather must be uniform, must be consistent or true. It shouldn't work for only the first element. It should work for all the elements present inside of the input. Now that we've talked about the rules, how about direction? So for the direction, this is the easiest part of mapping. You can see I'm coming from the input going to the output. If this is the input x, I'm coming from x, that is, it is this x, the input, that I'm applying my rows to, and then it is mapping out to the output. So 2 mapping out to 5, 4 mapping out to 11, 6 mapping out to 17. Under this row, 3x minus 1. So let's move on to the types of mapping that we have. We have 4 different types of mapping, 4 different types of mapping. And out of those mapping, only few or only some can be classified as function. The first type of mapping we want to talk about will be the one-to-one mapping. One-to-one mapping. So let's say we have 2 dots here, and then we have 2 dots here. So for one-to-one, we're simply saying one element of the inputs is mapping out to one element of the outputs, and so also this type here. So this is 1-to-1 mapping. Okay. Then the second type of mapping we want to talk about would be the okay. So this would be the many-to-one mapping. So we have this is mapping to this. This is also what mapping to this. Okay. So let's say this is many to one mapping, many to one mapping. Okay, so we also have the one to many mapping, one to many mapping. So this is mapping to many, so one to many. So we have something like this. Then we have something like this. So this is moving like this. This is moving like this. So this is one to many mapping. And then finally, we have the okay. So let's make it smaller. So this one we have the many to many. So this is mapping out to this. It's mapping out to this. This is also what mapping out to this, and this is mapping out to okay. So this is many to many. So this is many to many type of mapping. All right. So how do we what's it called? How do we distinguish between all these types of mapping? So you can see that for the first mapping, we have one input mapping out to a different output, or one input, one output, one input, one output. So when we have something like this, then we can refer to it as a one-to-one mapping. But if different inputs are mapping out to one unique output, you can see it for the many to one. So different inputs. This is one input. This is another input. Both of them are mapping out to the same output. Then it becomes many to one mapping or relation. Then we have the one to many. So one input mapping out to multiple outputs. So this is one to many. And for many to many, one input is mapping out to many outputs. One output also is coming from is as a result of many inputs. So this is many to many mapping or relation. So like we said, out of these four types of mapping, only two can be classified as functions. And why is that so? For function, we want to simply have a unique input and then a unique output. That is one input to one output, not one input to what's it called, to two outputs. So again, I repeat myself. For functions, function is like a printing machine or a money machine that you put in a particular value, and then each time you put in a particular value, you're having another value entirely. You're having a different output, not two outputs, not three, not multiple. One, two, one. So out of these types of mapping I've written, only one to one and then many to one would be classified as function. But I just said for function, it has to be one to one. Look at this. This is map. This is one input going straight to one output. This is another one input going straight to another one output. Of course, it is the same output, but then think about it that okay. So let's say I was to put in a value of one inside of this machine, and each time I put in a value of one, then definitely it should be the number I'm having should be two. Not that I put in one and then I'm having two sometimes, or then I have three another time. No, it has to be one or two. I can now put in another value. Let's say I put in two and then still have the same two. It still classifies as a function. So one unique input and then one unique output attached to that. All right, so I'm going to be cleaning this now, and then we'll look at how we can now represent what's it called, mappings, how to represent mapping, or how we represent. Okay, I think we can do that last at the end of the video. We can do that last, so we can just talk about function itself as a whole. Okay, so like we said, function is like a machine that you put in a particular input and then you have an output outside. Now, why is it that we picked what's it called, one to one and then many to one as a function? Now, before we can determine something to become a function, it must pass through the vertical line test. Vertical line test. The one-to-one type of mapping we did, it means that for every input I have a different and unique output. If I were to plot a graph of one-to-one inputs, then my graph will simply look like this. My graph will look like this, like a straight line. So if I were to draw vertical lines in such a way that the vertical lines looks like this, looks like this, looks like this, looks like this, looks like this. So we'll see that at every point in time, this x value here has a different y value. So this x, let's say it is -4. My y here, if this is my y axis, my y can be corresponding to another different value. So let's say -3. Now at this point here, let's assume that x is -3, -3. Y value at this point is no longer at -3. So let's say it is at -2. So if this is -2, let's say this y is be about -1. If x is 0, y is 0. So you can see that at every different point in time, x values, at every different point in time for my x value, I have a different and unique y value. So this is why we say this is one to one. So another way of representing a one-to-one mapping is by just drawing a linear graph or a straight line graph. So for a many-to-one graph, a many-to-one graph looks like this. You will have seen something like this before. Sorry about that. I've seen something like this before for a many-to-one graph. It looks like this. So many to one graph can be like this. Okay. So again, if we were to do our vertical line test, 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 vertical line test. So you see that at every point in time, at this junction, the x value corresponds to a unique y value. So not x having two or multiple y values. One x, one y. Again, at this junction, one x, one y. 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 But you can come to think of it that, okay, what if at this junction, let's say I were to do a particular point like this. So, and this is minus 2. So let's assume that this is positive 3 and then this is negative 3. So you can see by putting negative 3, it returns negative 2. Wow. Putting positive 3, also returning what? Negative 2. But the point is one input to one output, not one input to multiple outputs. So once that is true, then it can be passed along as a function. Now, how do we now denote functions? How do we write functions? So for function, we simply write them like this. We write it in terms of f of x. F of x, and f of x simply means f, then putting in brackets of x. How do we read this? We simply read this by saying f of what? Of x. So if I want to read this, I'll simply say my f of x. But this is not the only way to write this. I can also say f given that, okay, so let's do this properly. So f given that x is equal to a particular set of rule. So if you see a function written like this, the way to read it is f of x, and this one, this is f also of x, given that x is equal to some other option. So here they will have put a rule. So let's say we are given a rule as 3x plus 1. So either they write it like this, or they simply tell you that f of x is equal to 3x plus 1. So I hope this is clear. So that you are given f of x, or f of x given that x is equal to 3x plus 1. So sometimes you might be asked to put in values or find the value of x when x is equal to 3 or 2 or negative 1. It doesn't matter. So let's say we're given that f of x is equal to 3x plus 1, and then we're asked to find f of 3. So what we simply want to do is substitute the value of 3 inside of this function. So anywhere I see x, I'm going to write in 3 instead. So this becomes 3 in the bracket of 3 plus 1, and then 3 in bracket of 3, that's 9 plus 1, and this will give us what? 10. Sometimes you might be given another function, and then let's say this time around we're given it as a g or g of x, and then we're told that g of x is equal to x squared plus 1 divided by 2. And then we're asked to find g of negative 5. Again, what do we do? Instead of this x squared, I'm going to be putting minus 5 instead. So if I do that, then I have minus 5. Again, everything squared plus 1 all over 2. Okay, so minus 5 squared, that should simply be 25 plus 1. And 25 plus 1 over 2 is simply 26 over 2. And that gives us 13. So this is how we substitute values inside a function. And remember, for a function, we will either give you the what's it called? Let me clear this now. So for us to represent a function, either you are given the arrow diagram, the diagram of drawn, the one-to-one, the many-to-one. Either you have something like this, they can tell you something like this. So yeah, you have something like this. So you can either have this and this. You can give a function like this. You can also be given a function like this. Okay, and then this is mapping out to a single point here, a single point. So you can either be given a function like this. So this method of representing a function, refer to it as the arrow diagram method. Arrow diagram. Okay, so it can either be given to you like this, or it can be given as an equation. So remember the previous example we treated, we told that f of x is given as x plus 1. So f of x is given as x plus 1. So this is another way of representing a function. This method This is simply an equation. And then the third method of representing a function is by the graph. So I think we treated a linear graph. So either we have something like this or a quadratic graph or a quadratic graph. So we can be having something like this. So either you are given arrow diagrams, equation, or graphs. So you should be able to interpret it as function. So in our next video, we're looking at the meaning of composite function, and then we'll look at more examples concerning functions, given the role of the function or the equation of the function. Thank you and bye-bye.